All right, guys, this is Mr. Barone again. I'm at a point now where I'm actually trying to get ahead here, and I'm doing multiple of these videos a day. So if you see the same shirt and fancy tie, I'm not wearing it over and over again every day. I'm doing a couple of these every day. So we'll do another one of these videos. This will be the second lesson in kinetics. I'm going to pause the video and ask you guys to answer this do now question. So go ahead, give it a shot, think about it, look it up, then we're going to go over it. All right, so you guys should have had a few minutes to answer 34 and 35. Number 34, if an element, which group on the periodic table would a non-metallic element belong if an atom of this element tend to gain 2 electrons to complete their valence shell? All right, so we know we're dealing with a non-metal element. Which of those nonmetals want to gain 2 electrons to complete their valence shell? Well, it'll be group 16. We'll make our way over to the periodic table in a minute, but we'll talk about that. Group 16, they have 6 valence electrons. They need 2 more to make it 8 to complete their octet and to be stable or happy. So they need 2 more. Number 35, what trend is observed as the first 4 elements in group 17 on the periodic table are considered in order of increasing atomic number? This phrase, increasing atomic number, simply tells us that we are going to start at the top of group 17 and we're going to go down. So what happens from fluorine as you go down towards bromine? Well, we know that the electronegativity actually will decrease. We know that the first ionization energy, the amount of energy needed to remove the most loosely bound electron, that does decrease. So that's going to be your answer. So let's go through in 3 and 4 and make sure they're wrong. The number of valence electrons increases. That's false. If they're in group 17, they all have 7 valence electrons. Okay. And then the number of electron shells decrease. That's also false. We know that the number of electron shells will actually increase. Let's see if I can jump over really quick and show you. So here's that first question, group 16. So group 16 is here. They all have 6 valence electrons. They all need 2 more to get that last number in their electron configuration to 8. And 8 is the sign of a stable octet. So -2 charge, they all want to gain 2 electrons. Okay, similarly, if you were to go to group 17, what trend do you notice as you go from 17? Notice it says as you analyze group 17 in order of increasing atomic number. So we're starting with 9, and then the next one is 17, and then 35, and then 53, and then 85. So as we go in order of increasing atomic number, we're starting with fluorine and we're going down. Okay, and if you analyze on the next page, each of the characteristics that this question asks about, some of these we can stay here. First of all, they have 2 shells here, 3 shells here, 4 shells, 5 shells, 6 shells, etc. So the number of shells is not decreasing, it's increasing. The number of valence electrons is the same. And then if you want to go find out the last part, okay, you want to deal with what they're asking about electronegativity and ionization energy, you can look right here. Okay, so as I erase this, you can go to this table and you can analyze for yourself. You have ionization energy here and electronegativity there. We can find the first few elements and see if we can, rattle this off really quick, and then we'll pause it and get back into the lesson. So again, we were starting with fluorine. Let's see if I can preserve the circles. There we go. So we can look at the first few. You got fluorine here. Chlorine is here, and I don't know if we're going to get the next one. No, we're not. We can at least look at the first 2. Electronegativity you see is decreasing, so that's going to eliminate that. But ionization energy is actually going to, it says electronegativity is decreasing, but the answer choice was increasing. This one is actually decreasing, so that's why that was our answer. All right, so let me jump back to our slide. Now we did the do now. I do want you guys to take a look at this one really quick too. Okay, so I'm gonna pause the video, let you do the second question, and we're gonna go over it. All right, now I know, like I said, this seems silly, like we're gonna spend five minutes or so going over the do now, but this is your review. This is all the time we get together now, so it's important to review some of these. And I love this question. It looks like, again, it's a sheep in lion's clothing. It looks like it's a terrifyingly difficult question, when in actuality, it's pretty straightforward. All it's asking you to do is to go to table E, and match it up. It's really simple if you know that's what the question is asking you to do. So they give you a passage, they give you a chemical reaction, and then they give you the question. Based on table E, identify the polyatomic ion in the solid product of the reaction. Well, last lesson we learned about product. We know that products are these guys on the right side of the arrow. These are my products. They specify that we're dealing with the solid product. Well, this is a gas. That's not a solid product. This is a liquid. That's not a solid product. This one is. So you're narrowing down your choice now. So we have a solid product right here, an Na2CO3. So they want us to identify the polyatomic ion in Na2CO3. Well, on table E is CO3 minus 2. And that is the polyatomic ion that they want. I imagine if you wrote CO3 minus 2, that would be right. You could also have written the word carbonate, and that would be right as well. So I thought this was a really good question to go over. All right, transitioning on. Our objectives. You're going to explain various factors such as temperature, surface area, and concentration can influence the rate of reaction. And that's going to be something we call collision theory. And you're going to explain in writing whether a change would increase or decrease the rate of reaction, and explain why we're going to use this phrase, more effective collisions, in our answer. Here's your meme of the day. Enjoy. Let you guys soak that up. I like this one because I will probably continue doing this, and I probably won't get a reaction because it's just me on my computer right now. But I hope you're laughing at home or at least cracking a smile. All right, moving on. This is fun. This is a little turn and talk opportunity for you. I want you to come up with a way to dissolve a sugar cube as fast as possible. Now, you can even pause this for a minute and run your own little experiment. This is pretty harmless. You can go to your kitchen and get sugar cubes. If you don't have sugar cubes, you can get a spoonful of sugar or a spoonful of salt, and get a couple of them. Get a couple spoonfuls of sugar or a couple spoonfuls of salt, and see if you can make one dissolve really fast, and see if you can make one dissolve really slowly. What would you do to make one dissolve fast or slow? I'm going to pause the video. Maybe you want to pause the video too. You can either just think about this, you could look it up on your computer, or maybe you want to run to your kitchen and run a little experiment. What do you think would dissolve a spoonful of sugar faster? And what would make dissolving a spoonful of sugar take a very long time? So pause it, think about it, maybe go do a little mini experiment in your kitchen, and we'll come back and go over it. Okay, so we're back. And like I said, in class, if we were meeting in person, we actually have like a mini lab activity where we actually try to do this. I challenge kids to come up with one way to dissolve a sugar cube as quickly as possible in the shortest amount of time. And then also to come up with a single way to dissolve a sugar cube as slowly as possible. So again, if you want to pause the video and try to do this, could you dissolve a sugar cube in less than 10 seconds? Or could you dissolve a sugar cube in more than like 5 minutes? Something like that. Could you come up with something, and then do you want to test it? Go test it. And you can do the same thing with salt. If you don't have sugar cubes or sugar, you can do the same thing with salt as well. So I don't know, I'll pause the video again, see if you guys can figure this out, and then we're gonna go over it. All right, welcome back. Hopefully you at least thought about it. Maybe you even went and did a little experimentation yourself. I would imagine that you came up with some variables like hot water versus cold water. Maybe you crushed the sugar cube versus not crushing it. Maybe you stirred it, but didn't stir it for the one that you wanted to take more time. Maybe you used a lot of water for one and a little water for the other. There are a lot of variables that can determine how long it takes to dissolve a solid like salt or sugar. And we're going to talk about some of those things today. What are those variables? Well, we went over a bunch of them, and they all are addressed in this thing called collision theory. So you will need to write this down in your notes. Collision theory, the theory that the reaction rate will increase when there are more effective collisions between reactant particles. Okay, there's a lot here. Pause it, copy this down, and then we're going to break down parts of this definition before we go over some examples. So I'm going to pause it, make sure you write this down, and then be ready to talk about this some more. All right, welcome back. So there's a couple things. Remember, the reaction rate, that's how fast the reaction will happen. That will increase when there are more effective collisions. In order for a collision to be effective, you need two things. They need to be orientated properly, they need to hit each other in the right direction, and they need to have enough energy when they collide into each other. Okay, so they have to be facing the right way, facing the right way, and they have to have enough energy. So if they're moving very slowly, maybe they don't have enough energy to react. If they're moving, very quickly, they do. And if they're not oriented in the right direction versus something like this, that could mean something else entirely as well. So an effective collision has the right orientation, they're facing the right direction, and they have enough energy, meaning they're moving fast enough. So on a molecular level, this has to happen for a reaction to occur. And we're going to look at a reaction here between A2 and B2 forming two molecules of AB, a pretty typical general reaction. What I've done is we're going to do a thought experiment. So if I took a big box and I put all of the A2 on one side of the box and all of the B2 on the other side of the box, I have my two reactants separated by a wall that I can slide up and down. Okay, so right now they're separated and they can't collide with each other. So in other words, they can have no effective collisions because they can't collide at all. They're separated. When I remove this, now they're free to move about this box and collide into each other. We're going to talk about the various factors that can determine whether or not A2 and B2 will react to form AB. Okay, so I'm going to let you think about this for a minute. Let me switch gears here, pause, and look at the next few slides, and we're going to go over. Okay, so now here we go. Whoa, skip. What we're going to do is we're going to pull this up mentally. We're going to pull up this little wall that separates A2 and B2, and we're going to open up the whole reaction chamber, the whole box, and allow these molecules of A2 and B2 to start floating around each other and potentially collide. So if we do that, we pick up that wall, we remove the separator, and now we see something like this. A2 and B2 are now moving around this sealed box, and they are free to bump into each other, to bump into other A2s and B2 molecules. They are now free to collide. All right, so with all that, if you could imagine now that they're colliding, there are two things that can happen. If we go back to that term, effective collisions. An ineffective collision, if A2 and B2 approach each other like face to face like that, when they bounce off each other, that's not effective because they're not going to react. What's going to happen to this molecule, this atom of B and this atom of A? They're not oriented properly to form a reaction. However, if A2 and B2 approach each other this way and they collide side to side, now you see why this would make more sense for AB and AB to form, because they are now aligned properly where they can sort of react. So an ineffective collision is if they bounce off each other this way. Whereas an effective collision, they would bounce off each other that way. Also, ineffective collision, if they're not moving fast enough, if they don't have enough energy, that could be another reason why it's ineffective. Whereas an effective collision, meaning they would have enough energy. So how could you maximize the effective collisions between these particles? So here we go. Now you have A and B floating around. How do you maximize how often they will collide and possibly increase the number of effective collisions? What things could you do? So why don't you stop and think about that, look it up. What would you do if you wanted A2 and B2 to collide more frequently and to give you effective collisions so that they can react more quickly? All right, so collision theory says that there are a number of ways. We're going to start with 4. We might add a few more to this list in the coming days. But collision theory says there are a few ways to do this, to increase the rate of reaction or the speed of the reaction. 1, if you increase the temperature. 2, you can either decrease the volume of your container or you can increase the pressure. They essentially have the same effect. And for the first time we see pressure. We're going to actually start talking about pressure. You can increase the concentration. If you add more stuff, the likelihood that they will collide also increases. Then you can add this thing called a catalyst. And we'll talk about what a catalyst is. Maybe some of you people who work in the auto industry, you maybe heard of a catalytic converter where there's a part of that word there, and it certainly is related. So adding a catalyst is something that we'll learn about as well. We're going to go one by one through these, and then I'll give you guys a few videos, and there'll be an exit slip, and then that'll do it for today. First one, temperature. I will post these videos to the Google Classroom post that accompanies this video. But if you can imagine now that we're at 20 degrees Celsius and these guys are floating around like this, ready to bump into each other at 20 degrees. If we suddenly heat it up and they start moving faster, and we get up to like 90 degrees Celsius, now they're moving faster. The odds of them colliding is now increased. So by increasing the temperature, you are increasing the speed of these particles. And if they're moving faster, they are more likely to collide with each other because they're covering more space more quickly. So increasing the temperature is a surefire way to increase the rate of reaction because you have more effective collisions. If they're moving faster, they're going to collide more. If they're colliding more, you have a higher probability of getting more effective collisions. All right, number two, you could increase the pressure or decrease the volume. So right now you see this scenario, there's a lot of open space between the molecules. If we were to decrease the volume of that container, if we were to move them into a smaller container or increase the pressure, something like this. Let me actually delete this box. If you decrease the size of that container, now they're closer together. If you were to increase the pressure of that container, you would squeeze them together. So if you squeeze the particles closer together, then they are more likely to collide. If they're more likely to collide, they are more likely to have an effective collision. Secondly, or thirdly, I should say, you can increase the concentration. So if I only have, in this case, I only see 6 B2 molecules and 4 A2 molecules. If I dump in more of them, well, they're certainly more likely to collide with each other because now there's more stuff that's going to bump into each other. So increasing the concentration might look like that. So now if you add more stuff to the mix, suddenly now there is a higher likelihood that 2 of these molecules can collide properly. Lastly is a little bit harder to understand, adding a catalyst. A catalyst helps orient the molecules so that they bounce off each other in the right way. A catalyst is another molecule that really doesn't participate directly in the reaction, but it gets involved by allowing the reactants to collide in a way that is more effective. Okay, so those are the main ways that you can get more effective collisions. Okay, there's another video here that goes through all these together. I will post them all. They're all very good if you ask me. Now we're going to do a couple of practice exercises and then we'll give you guys your exit slip. So our objective is to explain in writing whether a change would increase or decrease the rate of reaction, and I would like you to explain why. And I would like you to use the phrase more effective collisions. So I'm going to pause the video, read this question, look at the reaction, and then answer this question down here, trying to use the phrase more effective collisions in your answer. All right, pause the video, think about your answer, have it in your head, put it in your notes, and we're going to go. All right, so what effect would decreasing the temperature have on this reaction between silver nitrate and sodium chloride turning into silver chloride and sodium nitrate? What effect would decreasing the temperature have on this? Well, when you lower the temperature, you are lowering the speed of the molecules. And when you lower the speed of the particles, you will have fewer effective collisions. You will have fewer collisions together entirely, and you will also have less energy within those collisions. So suddenly now you will have a decrease in the rate of reaction because you have fewer effective collisions. Okay, let's look at another one. Take a minute. Oh, we just went over that one. That's good news. We're making progress. Let's look at one more. Take a minute. Look at that general equation, AB turning into CD. I'm going to pause it and try to answer the question using your notes. All right, so using your notes, a catalyst will increase the number of effective collisions. So what effect would adding a catalyst have on the rate at which C and D are produced? Adding a catalyst would increase the rate at which C and D are produced because we would have more effective collisions. That's it. So that's what this lesson was all about, okay? Anytime you do anything that increases the number of effective collisions or increases the energy of those collisions, you will increase the rate of reaction. Anytime you make a change that decreases the number of effective collisions, you will decrease the rate of reactions. All right, I have an exit slip here. I will post this on a Google Doc. It's this T-chart here that's going to ask you to think about as many ways as you can to increase a reaction rate versus ways to decrease a reaction rate. Obviously, there'll be opposites. If one thing over here increases the rate of reaction, like for instance, temperature, if you do the opposite to the temperature, that should decrease the reaction rate. So I want you guys to put together a list of all the ways to increase and decrease reactions. And I'm going to ask you a question like you saw at the end of the lesson, okay? Our objective was to Explain how various factors such as temp, surface area, concentration, catalysts, etc., can influence the rate of reaction. And you are trying to explain in writing in your exit slip whether a change would increase or decrease the rate of reaction. All right, guys, check out your exit slip. I'll post all the videos, the YouTube videos that were also a part of this presentation along with this. And please submit that exit slip at the end of this lesson. It will be due by the end of the day. And I'll see you guys tomorrow.